Once you've determined the shape of a molecule, you can tell some things about it. And one of the things you can tell is whether it's polar or nonpolar. This has a huge impact on what it reacts with, and so this is an important concept. Now, we have two different things here. We can talk about the polarity of a bond, and we can talk about the polarity of a molecule as a whole. The first step in determining whether a molecule is polar is looking at its bonds. And then, based on its geometry, you can determine whether the molecule is polar or nonpolar. So first, let's look at the bonds here in silicon dichloride. Chlorine is more electronegative than silicon, and so it will actually hold a larger portion of the electrons closer to itself than silicon will. And we can quantify how much it is by looking at what we call a table of electronegativities. If we look at the table, we see that chlorine has an electronegativity of 3, and silicon has an electronegativity of 1.8. Actually, just subtracting those values, we can calculate what we call the bond character, or the polarity of the bond. If that number right here falls between 0 and 0.4, we call it a pure covalent bond. That means for all intents and purposes, those electrons are shared equally. If it falls between 0.4 and 2.0, then it is what we call a polar covalent bond. So it's still a molecular bond, they're still being shared, but they're shared unequally, and we call that polar. If the bond is greater than 2, then we consider it an ionic bond. So we consider the electron to be completely transferred to the other side. So if we go back to our silicon tetrachloride example, the bond falls, the difference in the electronegativities falls exactly at 1.2, which is right here in the polar covalent range. That means that the electrons will be shared unequally, but they're still shared. Now we can draw what we call a dipole moment towards the more electronegative element. We said that chlorine had the electronegativity of 3.0, so that means that each chlorine will pull electrons away from the silicon. So that means that we have polar bonds. But we also want to determine, and more importantly, whether we have a polar or a nonpolar molecule. Since each of these is pulling away from the silicon in a very symmetrical way, it actually ends up with what we call a nonpolar molecule. So you need to take into account whether the bonds are nonpolar or not, and the symmetry of the molecule. Since each of these chlorines is pulling in equal and opposite ways, that makes this molecule nonpolar. Now that can be counterintuitive, so let's look at a couple more examples. Here we have silicon dioxide. Let's first look at the bonds between silicon and oxygen. If we look at their electronegativities, oxygen has 3.5 and silicon has 1.8. So let's subtract 3.5 minus 1.8. It gives us 1.7. So that is a polar covalent bond. This is between 0.4 and 2.0. That makes it polar covalent. So then we can draw the direction of the dipole moment towards the more electronegative element. Since oxygen had an electronegativity of 3.5, it's more electronegative than silicon with an electronegativity of 1.8. So we draw those lines towards the oxygen. In this example, it's easier to see that these dipole moments are pulling in equal and opposite directions. If you were to play tug of war and both sides of the rope were pulling equally and they're pulling exactly opposite of each other, the rope wouldn't go anywhere. Since the rope doesn't move, that means that the molecule overall is nonpolar. If one of them were to pull stronger than the other, then it would be a polar molecule. if that rope were to move. For example, let's look at nitrogen trichloride. So nitrogen has an electronegativity of 3.0 and chlorine has an electronegativity of 3.0. So if we were to subtract those from each other, we get an electronegativity of 0.0, which means that we have non-polar bonds. These bonds are equally sharing those electrons. But what we have is we have a lone pair up here. And that lone pair on the nitrogen pulls in a similar way to how and so we can draw a dipole moment pointing towards the electron pair. That gives us an overall dipole moment for this whole molecule, which means that the molecule is polar. So you see here in the silicon dioxide example, we had polar bonds but a nonpolar molecule. In the nitrogen trichloride example, we have nonpolar bonds but a polar molecule. So sometimes these will be the same and sometimes they won't. It really depends on the geometry of the molecule. Let's look at oxygen dichloride. So if we look for the electronegativities of oxygen dichloride, we can find oxygen with 3.5 and chlorine with 3.0. Since oxygen had the greater electronegativity, we're going to draw the dipole moments pointing towards oxygen. And we can look at these as if the lone pairs as if they were dipole moments as well. It's not the technical way to think about it, but it won't steer you wrong if you think about it that way. And we see that there's an overall dipole moment pointing upwards here. So these on the top from the lone pairs are pointing out, while the chlorines are pointing from the chlorine are pointing in, so the x-axis part of this vector is canceled out, but all of them are pointing up, and so we have an overall dipole moment pointing up. So we have polar bonds because of the difference in electronegativity here, and we have a polar molecule because there's an overall dipole moment pointing up. And lastly, let's look at a more complicated example of sulfur dioxide. First, we'll look for the electronegativities. We find sulfur with an electronegativity of 2.5 and oxygen with an electronegativity of 3.5. So we subtract 3.5 from 2.5 and we get 1.0, which means we have polar bonds because that number is between 0.4 and 2.0. Now we can draw the dipole moment pointing towards the more electronegative of the elements, which is oxygen. But we can also draw a dipole moment point towards the lone pair. Now you can see that it's hard to tell without knowing just how much it's pulling up whether there is an overall dipole moment or not. So we've got a net one going this way and a net one going this way. And whether or not they cancel each other out is hard to say because we don't know how strongly that electron pair is pulling. So we don't know if it's polar or not. We would need some more information. And that information is found experimentally.